today is something that you have hopefully seen in other courses. Tell me if I'm wrong, but you guys know that if we have a right triangle, okay, I guess you guys can't see anything yet. Okay, if we have this right triangle and I call this A, and that B, and that C, there's a relationship that links those three parts together. What's that relationship? A squared plus B squared equals C squared. Okay, what's that called? All right, that's the Pythagorean theorem. Okay, now the Pythagorean theorem, there's, how we've done proofs, and there's proofs for this, and we, maybe if we have time after the end of the course exam to go back and prove this. But we've talked about how there are proofs that, theorems that we can prove maybe multiple ways, right? Okay, using different approaches. There are, I think, the number, it might not be an exact number, but I'm ballparking from what I've read in the past. I believe there's like 37 adequate true proofs for this theorem. Okay, so a lot of different ways to view it, think about it. But we know A squared plus B squared equals C squared. Okay, what that means to us is if I take, let's just do an example real quick. And there's going to be some vocabulary here that we need to talk about as well. I'll briefly introduce. Let's say this is 3. That's 4. This is 5. Okay, my question is this a right triangle? Well, if it is a right triangle, it's going to have to satisfy that relationship, right, or that equation. Every single right triangle, this will be true about. Okay, so what would A be in this case? Okay, 3 is fine. What's B? 4. Now, because addition is commutative, those two things could be flip-flopped, right? A could be 4 and B could be 3. Doesn't matter. But what would C be? 5. Okay. What is 3 squared? 9. What's 4 squared? 16. Does that equal 5 squared? Yes, that is true. So, this is a right triangle. All right with everybody? Okay. When you satisfy that, you create a right triangle. So this is what we've referred to as a 3, 4, 5 right triangle. Okay. And there's a lot of like real life applications for this. If ever I want to know, like let's say that I'm building a house or something like that. I'm a contractor, and I want to know whether the structure that I'm about to put up is square. Okay, have you guys ever heard that word? We say something is square. That meaning that it's perpendicular. The sides are perpendicular. What a lot of contractors will do is, let's say I have come up with some walls here. All right, so kind of have right now kind of the bird's eye view of two walls coming together. Okay, and you can view this as anything that might incorporate a right angle. Maybe I have a piece of plywood. And I want to see if this is a perfect right angle, or maybe a piece of tile or something like that. Somewhere that you want to measure something to figure out if it's a right angle or not. What we have is the idea that a 3, 4, 5 triangle should exist here in this right angle. So what they do is they take their tape measure or whatever, and they go out 3 feet, okay, and they put a point on the 2x4s of the wall or whatever, or drywall. Okay, they just want to go out 3 feet, and then they're going to go on this wall, and they're going to measure out 4 feet. If this is a right angle, if that's 90 degrees, what should that distance right there be? Careful. It should be 5 feet, right? So they make these marks on the wall, there and there, and then they take their tape measure and hold it at B and pull it towards C, and if it measures out to be 5, that tells them that is exactly a right angle. Does that make sense? And they didn't have to have a protractor or any angle measuring device to do that. They just used distances to do that. Okay? Now, it doesn't have to be feet. It could have been, they can measure out 3 inches and 4 inches. Okay? Usually, a little bit of a larger distance is going to allow a little bit better accuracy with the devices that we use. But they're going to go on. Let's think about this. Could they go on 6 feet and 8 feet? 6 feet and 8 feet. That's 6. And that's 8. What would they have to measure across the diagonal? Or not diagonal, hypotenuse. That's 6. 6 squared. That's 8. 8 squared. What's 6 squared? 36. What's 8 squared? 64. What's that equal? 100, right? So square root that. What should my hypotenuse be? The hypotenuse should be 10. So they can go 6, 8, and 10. Okay. Well, 6, 8, 10. Isn't that just a multiple of 3, 4, and 5? Take 3, 4, 5 and double it. You get 6, 8, 10, right? Take 3, 4, 5 and triple it. You get what? 9, 12, and 15. Well, think about what 9 squared is. What's 9 squared? 81. Okay. So 81. What is 12 squared? 144. What is 15 squared? 225. Is that true? Is 81 plus 144 equal 225? Yeah. Okay. So 9, 12, 15 is another version of 3, 4, 5. It's just a multiple of 3. However, what I'm trying to get at here, what we'll talk about, is when you have integers for A, B, and C, and they satisfy the Pythagorean theorem as a group of 3. So that group of 3 numbers, okay, is referred to as a Pythagorean triple. Okay, Pythagorean triple is when your 3 values that satisfy the equation a squared plus b squared equals c squared are all positive integers. Okay. Last class we kind of looked at a few, and you're going to see enough of these, I think, in the next couple weeks that you're going to commit a lot of them to maybe memory. So let's see if we can get a list here of Pythagorean triples. Zoomed in real far. Okay, now, the way we're viewing it, okay, we want a triangle, but 1 squared plus 0 squared does equal 1 squared, right? And by definition, those are all integers. So this 1, 0, 1 is a Pythagorean triple. But the first one, the reason we like to talk about a 3, 4, 5 triangle is because side lengths of 3, 4, 5, those are the smallest, collectively, the smallest group of integers you could have. That we're going to form a right triangle. Okay? But 5, 12, 13 is another list. 7, 24, 25 is another list. 9, 40, 41 is another list. Okay? And those lists are generators. Okay? Well, what I mean by that, you don't see 6, 8, 10 in that list, right? Because 6, 8, 10 are generated from 3, 4, and 5. Okay? You don't see 9, 12, 15 up there because they're generated from 3, 4, 5. So if we look at that list, any multiple, okay, it might be, maybe, you don't have to write this down or anything, but maybe 3n, 4n, and 5n, where n is just any number, any real number it wants to be, will create a right triangle. Okay? 5n, 12n, 13n will create a right triangle. Okay? Now, if I want to maintain the Pythagorean triple idea, we would want n to be an integer. All right? But if n is any real number, you still would end up with a right triangle. Okay? Does that kind of make sense? Okay. So if at any time throughout Math Excel and of course exam, they use that phrase Pythagorean triple, they're referring to a set of numbers that satisfy a squared plus b squared equals c squared. Okay. One thing I want you guys to understand, though, is that the largest number in the list has to represent the what of your triangle, the hypotenuse, okay? You do get tricked every once in a while. They try to trick you by doing something like this, where they say, like this is 3 and that's 5. Can my hypotenuse be 4? No, it's got to be the longest side, right? So that's not a 3, 4, 5 triangle, okay? So just because you have 2 values out of the triple doesn't mean the hypotenuse is always going to be that third one. They have to be arranged that way if we have that triangle aspect to them. Okay, does that make sense? Okay. Just do a quick couple examples here. If we have this side length to be 6, this side length to be 3, can we find C? Okay, what would 6 squared be? Okay, what would 3 squared be? Okay, so we get 36 plus 9 is equal to C squared, right? What's 36 plus 9? 45. So we get 45 is equal to C squared. So what's C? Square root of 45 initially, right? Will we ever want that as an answer? Yes, we want to reduce this, so it turns into radical 9 times radical 5, doesn't it? But what's radical 9? 3. Okay, so 3 root 5 would be that hypotenuse. Okay, and guys, we want to keep it as 3 radical 5. We don't want to change that to a decimal, because once I change that to a decimal, then I have to round it, right? That's what radical 5 is irrational, so at some point I got to cut it off and round. That distance then is not going to satisfy the Pythagorean theorem. Is that all right? Because we want these exact values. So you guys have done that, right? That's not extremely difficult. Okay, I've seen that maybe in the 8th grade, 7th grade, 9th grade. What if I change things around a little bit? What if I give you this to be, let's say 6 again, but now let's say this is 8. Can you find that distance there? How do I do that? Good. Okay. Remember, when doing the Pythagorean theorem, this is one of the places that I get a lot of people get confused, is that they always want to take the 2 parts that they gave you and write those as the sum over here. Okay. But you can't do it because the Pythagorean theorem, A is a leg, so it's leg squared. B is a leg, so it's plus leg squared. And C is always your hypotenuse squared. Okay, so you need legs on both on this side over here, right? So right now we're seeing 6 and x being our legs. So we get 36 plus x squared equals a squared. 64. So x squared then is going to give me a 28. Is that right? Okay. So x is going to be root 28. But 28, what's the perfect square inside 28? 4, right? So 28 is the same as radical 4 times radical 7. What's radical 4 same as? 2. Oh. So 2 radical 7 should be that length there. All right. Is that something we can do? What if I asked you this question? What if I said, determine the type of triangle as acute right or obtuse based only on side lengths. So I'm not going to know right now because we don't have the math. I don't know how to find angle measurements, okay? But we should still be able to determine if this is going to be a right triangle or not. If I give you a side length of, let's say, 7, 10, and let's go 13. Okay. Now I know this is going to be a triangle. Those three segments will work. If you remember what we talked about in I think it was chapter 4, that the smallest two sides had to add to be something greater than the third side, right? But is this a right triangle? That's the question. Okay. Well, if this is going to be a right triangle, this is going to have to be your hypotenuse, wouldn't it? Does that make sense? So we're essentially asking, is this angle down here, is that a right angle? Well, if it's a right angle, shouldn't I be able to take 13 squared equal to 7 squared plus 10 squared? Does that make sense? Okay. What is 13 squared? 169. Does that equal 49 plus 100? No. Okay. So, what's that tell you? Not a right triangle, right? Okay. Because this right now, we have c squared. We're asking, is it equal to a squared plus b squared? So, and actually, let me write that in blue. I'm going to write some rules here. Come on. There we go. If I write, obviously, c squared is equal to a squared plus b squared. Okay, that would be, if that's satisfied, we have a right triangle, correct? But if they're not equal, isn't there an option that if they're not equal, then c squared would be less than a squared plus b squared? That's an option for things that are not equal, right? Okay. But another option would be c squared is greater than a squared plus b squared, right? Okay. Now, to distinguish this and to answer this question of whether something's a right triangle or not, I like to have my C, my hypotenuse, or my longest side first, because then it makes it easy to, I think, logically make an argument. Because when you see less than, okay, because if it's not right, it's got a chance of being acute or obtuse, right? Which one of those words would you associate with less than? Obtuse or acute? Acute. So this is going to be acute. And then if c squared is greater than the sum, you would have obtuse. It's not as easy, I think, logically to make that argument if you write things as a squared plus b squared and then either equal, less than, or greater than c squared. Okay, I can c squared come first. So if you can remember those rules, it tells you whether this is an obtuse or an acute triangle. So is 169, is it equal, less than, or greater than 149? It's greater than. So your c squared is greater than a squared plus b squared, so that triangle would be a what? It'd be an obtuse triangle. Okay? And we're going to actually have enough information soon, towards the end of this chapter, that you're going to be able to tell me what each one of those three angle measurements are based off the 7, 10, and 13. That's kind of where we're going with this stuff. Okay? So that's everything we know about right triangles. Okay, and you're going to get questions that deal with that. Right now, what I've decided to do in Math Excel, I've opened up an 8.1 assignment. It's not due till Friday. Okay, give you plenty of time to work on that. We're not going to see a lot of examples in class right now today over 8.1, but we'll see more throughout the week here with Pythagorean theorem, and hopefully maybe it kind of generates some thought and some ideas that you can complete that assignment by Friday. If you got questions, come see me. Come ask them during class. Ask them during walk-in time. I believe 8.1 open until Friday. Everyone okay with that? Tonight you're also going to have 8.2. 8.2 is due tomorrow. And that's really what I want to focus on today, is 8.2. But 8.2 is a direct It's a byproduct of what the Pythagorean theorem is saying for us. Okay, so 8.2. 8.2 is referred to as special right triangles. Special right triangles. And there's two types of special right triangles. So today we're only going to deal with half of 8.2. The first triangle is a 45, 45, 90 triangle. And then tomorrow we'll talk about what we call the 30, 60, 90 triangle. But what do you think those numbers represent? Those are your angles. So, okay, now if we're dealing with a 45, 45, 90 triangle, that's the only one we're going to talk about today. Okay? If you know two angles are the same in a triangle, you should know another way of classifying that triangle. It's based off sides. It would be isosceles. Good. Okay? So a lot of times, if they don't use the word 45, 45, 90 or the phrase 45, 45, 90, they might say you have an isosceles right triangle. Okay? That's the exact, that's a synonym for 45, 45, 90. Is that right? Okay. You know what a synonym is, Cam?
Yeah.
What?
Things that are somewhat similar.
No. It's a spice.
Did you say synonym or
Yes.
which one? Cinnamon or cinnamon?
I don't know. What is cinnamon? What is cinnamon?
Cinnamon is a spice.
Yeah, but where's it come from? Do you know?
Ginger.
Ginger. And then what's ginger? Where does that come from? Cinnamon?
Ireland.
You guys know what cinnamon is?
What is that racist?
Cinnamon is bark off a tree, off a cinnamon tree. I think it's a cinnamon tree, but it's bark. All right, so 8.2, special right triangles. If I have a 45, 45, 90 triangle, let's see what Pythagoras tells us. Okay? Let's just do a specific example. Let me give you this to be 3, that to be 3, and I want you to find what C is. So how would you do that? Three squared plus 3 squared equals C squared, right? Now that's 9 plus 9 equals C squared, right? Now some of you might want to write that as 18. That's fine. Is 9 plus 9 the same thing as 2 times 9? I'm going to write that way. You can do it however you want to, but I'm going to write that way because when I square root both sides, it's eventually going to turn into something like that, right? What's the square root of 9? 3. And the square root of 2 is just root 2, right? So there we see C to be 3 radical 2. Let's do another example. And that's just Pythagorean theorem, right? That's something you guys can do. You've seen before. Let's say that I have a right triangle, still 45, 45, 90. So let's say that this is 4 and 4. Let's find C. So we would go 4 squared plus 4 squared equals C squared, right? What's 4 squared? 16, right? Okay. Now, instead of changing it to 32, can I go, if this is 16 times 2 is equal to C squared? Square root both sides. What's square root of 16? 4. What's the square root of 2? The square root of 2, right? So now we see C is equal to root 4 over 2. Okay? Humor me here. What if we did 5 squared? What if this side here was 5 and this side was 5? Are you going to get eventually 25 times 2 is equal to c squared. What's square root of 25? 5. Square root of 2 is square root of 2, right? So if the sides are 5, the hypotenuse is 5 radical 2, correct? So what are you seeing here? What's the pattern of how that number there, which is the same as that one, relates to that one? How that one there, which is the same as that one, relates to that one. How, if I have the side length, let's say that I give you a side length of 13 for a leg of a right triangle, 45, 45, 90 triangle. I tell you the side lengths are 13. What do you think the hypotenuse is going to be? 13 radical 2. Okay? Now, we're only showing specific cases. We need to show a general case to see if this is actually a theorem, something we can use to expedite our workforce eventually. So let's see if this can be generalized. Okay? So if it's going to be generalized, that means we really have to take out all numbers. Okay? And we were starting with 3s or 4s or 5s for the sides. Let's take those numbers away, and let's just start with an arbitrary value n. Okay? Where, we might want to make the comment that n belongs to your real number. So it's any number that you can think of, but the relationship would be that they're the same, right? Well, Pythagoras says, if I want to find, I'm just going to write this as, I'll just call it C again. If I take C squared, the hypotenuse squared, that should equal n squared plus n squared, right? Is everybody okay with that? How many n squared does that give you? Remember, this was 9 and 9, or 16 and 16, or 25 and 25. It gave you 2 of them, didn't it? Gave you something like that. Does that make sense? Okay. Then to solve for C, we would just square root the left-hand side, square root that, right? When I square root the right-hand side, doesn't it become square root of 2 times the square root of n squared? When I have a perfect, because n squared is now a perfect square, right? Does that make sense? What's the square root of a perfect square? It's just this, right? It's just n. So those two things, the square root and the power of 2, cancel each other out. And you're left with root 2 times n. I don't like writing it that way. I'm going to put the n out front. So n radical 2. So this hypotenuse here is n radical 2. What does that prove? What argument we were trying to state? That whatever the side length is, the hypotenuse is that side length times radical 2. So if this was 3, 3, this would be 3 radical 2. 4, 4, 4 radical 2. Is that all right with everybody? Okay. So that's a theorem that we can use to just quickly, and it's just a Pythagorean theorem, but it allows us to quickly generate all 3 sides of a 45, 45, 90 triangle. Now, it only works with 45, 45, 90. So you got to make sure that you do have those components. So if I say this is 7, and that's 7, this would be 7 radical 2, right? Okay. If this is 17, 17, 17 radical 2, right? Let's say, now this n could be any real number we could ever imagine. Okay. So there are some real numbers that we don't really like very much, but hopefully throughout this course and the remainder of the course, we start to develop an appreciation for them. But that's a number that we don't necessarily like a lot of times because of how it behaves. But that's pi, right? So pi radical 2, correct? Does that make sense? Okay, some other numbers that are like pi that we don't really like. Radical 3. If that's radical 3, this would be radical 3, radical 2, right? Does that kind of make sense? Saying that same phrase to myself over and over again. But now, what is radical 3 times radical 2? Radical 6. Okay? That's the way we would write it. We never write our answer as an implied multiplication of radicals, we go ahead and multiply them out. What if this was radical 6, radical 6? This would be radical 6, radical 2, right? Which turns into radical 12, which now, when you multiply radicals, guys, you always want to pay attention to this, okay? Because, essentially, it's because this 6 has a factor of 2 inside it. When you create this 12, which is a larger composite number, chances are you have put a perfect square inside there, okay? Is there a perfect square that's inside 12? Yeah. So I can rewrite 12 that way, right? The square root of 4 is 2. So we want to write our hypotenuse as 2 radical 3 in that case. Okay? So the task or the goal here, and hopefully what you guys are recognizing, is that whenever you have a side length, whenever you have a leg, or a 45, 45, 90, to find the hypotenuse, you simply multiply by radical 2. Okay? Now it's really easy when your legs are integers, okay, or even if they're fractions or whatever, usually just slap on the radical 2. Okay? But if they start off as radicals, your leg is a radical, you actually have to go through that algebra, multiply them together, and then simplify. Okay? Now, what I want you to understand is that the hypotenuse is 2 radical 3. There is a radical 2 that's incorporated inside there. Does that make sense? Okay. Now, what they also can do to us, which is where people usually struggle, is that they start giving me triangles that again are 45, 45, 90. But now they give me this thing here to be, let's just say, they give me the hypotenuse. If they give me the hypotenuse, how can I work to get the side lengths? Okay. And if the hypotenuse is provided with a radical 2, does it make sense to you that this side here has to be a what? That has to be 10, and that has to be 10, right? Take a side length, multiply by radical 2 gives you the hypotenuse, right? So the argument here is if this side length has a radical 2 attached to it, if the hypotenuse has a radical 2 attached to it, then the leg lengths are just the coefficient out front, right? But why? Yeah, I want to show you the algebra of why that is. If I started in this triangle here, and I wanted, like the last examples we were doing, if that was 3, you multiply that by radical 2 to get the hypotenuse, right? Well, now I'm starting at the hypotenuse and I'm working the other direction. So what operation is kind of the other direction of multiplication? Division, right? So when I go from side length to hypotenuse, I'm going to multiply by radical 2. If I go from hypotenuse to a side length, I'm going to divide by radical 2. This is the way I kind of view it, guys. Every time they give me a triangle, I should be able to take, see if I can, oh, I can't group these. I should be able to take this picture here, okay, and redraw it so that it is congruent to the picture they gave me. So let's say I did. They gave me this picture. I redraw this one so it's congruent. If they're congruent, wouldn't this side length right here be the same as that one? Does that make sense to everybody? So doesn't it mean then that that distance right there would be the same as that one? If they're the same, can't I write the equation n radical 2 equals 10 radical 2? Now, once you get in the habit of doing this, because of what we're going to do tomorrow with the 30, 60, 90 triangle, now that I have this, you have the ability to solve for n. This is a coefficient. How do you get rid of that coefficient? Divide by it, right? So that division is going to give me 1n. Dividing the left-hand side by it, we'll have to do the right-hand side. Same thing, right? Divide by radical 2. Do those cancel? It's the only thing you're left with. 10. And n is 10, and n represented those side lengths. Okay? Now, hopefully you guys agree that this isn't too bad when, let's say that I put 13 there. What would this side length here be? This would be 13, right? Just take that number out front, pluck it off, and that becomes your side length. But when you see stuff like this, what do I do if this is 8? Now you don't see the radical 2 there, right? The radical 2 has already been multiplied through by something to generate this 8, okay? This is where you've got to take this template, that's why I call this blue thing right here a template, and say that n radical 2 and this 8 are corresponding congruent sides. So if that's the case, I should be able to take n radical 2, set that equal to 8, right? How do I solve for n? Divide by radical 2, and then divide by radical 2, correct? So n becomes 8 over radical 2. Now, do you like writing that way? No. Every time we type this into Math Excel, it's going to say you're wrong because you got a radical in the bottom. So if you remember from what we talked about last week, we got to multiply by that fraction, right? Whatever that radical is, you multiply by that over itself. That rationalizes the denominator. It gives me 8 radical 2 over, what's radical 2 times radical 2? It's just 2. Okay. Now, just kind of break things up here to prove a point. Can you do that? If I take 8 over 2 times radical 2 over 1, does that still give me this same thing here? So that hopefully proves a point to me that that can turn into what? What's 8 divided by 2? 4. So those things can cancel. It leaves me 4 root 2. And that then becomes that side length. That's because that's what I've solved for n, right? Solve for n, it's 4 root 2. So if they give you the hypotenuse, all you got to do is divide by radical 2 to get the side length. Okay. Is that something we can do? Now, I think a lot of you are going to see some relationships here that you can kind of maybe cheat the system. Because think about this. What if this was 18? The only thing that would change would that be an 18, right? This would be an 18. So now you get 18 divided by 2. Well, what's 18 divided by 2? It'd be 9. So now this side length would be 9 radical 2. Does that make sense? Okay. If this was, 10, then that would go to 10. That would go to 10. That would go to 10. But now it's 10 divided by 2. It'd be 5, right? What do you see in the relationship here when they give me that as, I'm going to say an even integer? How do you get the side lengths from it? Cut it in half and multiply by radical 2, right? Okay? Or cut it in half and slap on radical 2, however you want to view it. Okay? Now, does that work if that's odd? Let's say this is 11. So this would be 11, right? This would be 11. Now I get 11 radical 2 over 2. Do those reduce? Is 11 halves divide evenly? Is 2 going 11 evenly? No. So do not write this as 5.5 radical 2. You rewrite it as, keep losing my cursor. Keeps dying on me. There we go. You just write it as 11 halves radical 2. We write it that way. Okay. Does that make sense? Okay. But here's where, and we'll get maybe 1 or 2 examples of this. Here's where it becomes a little trickier, and why I want you to be able to do this algebra over here is because a lot of times they won't start you off with an integer as the hypotenuse. They'll start you off with like something like radical, let's say, let's just do 6. I think we've already seen this one, but they give me that. It's not as easy now as cutting it in half and slapping a radical on it. Okay, so we want to say that this segment here, this radical 6, corresponds. Hold on a second. I don't know why this does this. All right. This radical 6 corresponds to this n radical 2, right? So I'm going to create that little equation that says n radical 2 is equal to radical 6. So how do I solve for n then? I'm going to divide by radical 2. Divide by radical 2. And that gives me n to be root 6 over root 2. Now that is an answer. But it's not an accepted version of it. Does that make sense? So what do I need to multiply by to get rid of that radical 2? Radical 2 over radical 2, right? What's that give me up top? Radical 12. What's that give me on the bottom? 2. Okay? Now that's an answer, but it's usually not an accepted version of it because of that 12 being able to be rewritten as good 2 radical 3. Now what's going to happen with those 2's? They can drop out, and you're left with then radical 3 as n, right? Okay. So there's going to be time, and this is where I said a couple months ago, radicals are going to be a big component for the rest of the course, right? If you can't multiply, rationalize, that kind of stuff, radicals, add together, simplify, you're going to struggle a lot with the stuff that we do in this section. And then if we have 40 sections left over the remaining year, or remainder of the year, I would say that special right triangles are incorporated in at least 30 of those homework assignments. Okay, so please learn this. Okay, I think two of the most important things that you guys discuss in high school math that is used consistently through all of high school math beyond this point and all maybe college math that you undertake. Number one thing I think is factoring. Okay, learn how to do that, and it's going to set you up to be successful in a lot of other places. The number two thing is special right triangles. Okay, how frequently they're used, how much we use them in trigonometry. The entire trigonometry course is kind of based off of those two triangles, and everything that we do in that course is based off those two triangles for the most part. There's an assignment in Math Excel, 8.2, due tomorrow. Basically, it's giving you a picture like that red triangle and saying find a side leg, okay, find a leg. Or it's giving you legs and says find the hypotenuse. Okay, there's about 20 some odd questions that do that in. We'll see if we have questions over that tomorrow. Usually there aren't questions about this by itself. It's when we start talking about the 30, 60, 90 triangle that we run into a little bit of an issue. But we'll try to use the same approach as that tomorrow. If you can use the same approach, I think about the template idea, matching things up, creating those little equations. The 30, 60, 90 is not too hard. You got a question?
No.
Just want a high five?
Yep.